Hi, thanks for joining me. Today I'm going to be going a really cool IMO problem, and thankfully it doesn't take that long to solve. And the reason I chose this problem is because in the solutions, the first line is to try the dumbest thing possible, which when I read gave me a little chuckle. So what's the problem? We have A2, A3 all the way up to AN. Notice we're starting on A2 here. Are positive reals and they have a product of 1, so they multiply to 1, and N here is at least 3. We want to show that 1 plus a2 squared times 1 plus a3 cubed times so on all the way up to 1 plus an to the power of n is strictly bigger than n to the power of n. And yeah, I guess if you want a hint, try the dumbest thing possible. If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so this solution here relies on the AM-GM inequality, so the arithmetic mean geometric mean inequality. And this says that if you take the arithmetic mean of n numbers, so that means you add them up and you divide by however many numbers there are, that's going to be bigger than or equal to the nth root of the product of those numbers. In other words, the geometric mean of those numbers. And for this to be true, we need that xi is all at least 0. And also we can say that if we want equality to occur, in other words, this side to equal this side, we need all of these xi's to be the same. So if you've not seen this result before, I encourage you to look up what this result is and how it's proved, but I'm just going to be using this here, and this is a pretty standard thing to use in these sorts of exams. Okay, well, how am I going to use this here? Well, what I'm going to start by doing is look at the arithmetic mean of 1 and a2. So 1 plus a2 over 2 is the arithmetic mean, so by the AM-GM inequality, this must be bigger than the square root of 1 times a2, which is a2. And now if I just rearrange and simplify this, I get that 1 plus a2 squared must be at least 2 squared times a2. Okay, cool. I'm going to do something similar with a3 now, but instead of thinking of 1 plus a3 as 1 plus a3, I'm going to think of it as a half plus a half plus a3, and then divide it by 3. And so this is now the arithmetic mean of a half, and a3. And then this is, by the AM-GM inequality, is going to be bigger than or equal to the cube root of a half times a3, which would just be a3 over 4. And so if I just rearrange and simplify this, I get that 1 plus a3 cubed is bigger than or equal to 3 cubed over 2 squared times a3. Okay, let's get another inequality here. Let's do something similar with a4, and you might be able to guess what I'm going to do here. I'm going to write it as a third plus a third plus a third plus a4, and divide that by 4. And so this is still 1 plus a4 on the numerator, but applying the AM-GM inequality, this is going to be bigger than or equal to the 4th root of a third to the power of 3 times a4. That's 1 over 3 cubed times a4. And again, rearranging this is going to give me 1 plus a4 to the power of 4 is bigger than or equal to 4 to the 4 over 3 cubed times a to the 4. And now we can continue in this way, and you notice that these inequalities that we're deriving here has 1 plus a2 squared, 1 plus a3 cubed, 1 plus a4 to the 4, and so on. And if I continue doing this, I'd eventually get 1 plus an to the power of n is bigger than or equal to n to the n over n minus 1 to the n minus 1 multiplied by an. Okay, if I call this product over here that we're trying to prove is bigger than n to the n, if I just call that, I don't know, x for now, what I notice is if I multiply all of these left-hand sides together, I get x. And because everything here is positive, I don't have to worry about signs of these inequalities flipping about. I can just multiply all the left-hand sides and conclude that that must be bigger than or equal to the product of the right-hand sides here. And so if I just do that over here, x must be bigger than or equal to what I get if I multiply this term by this term, and so on all the way down the list. Oh, I forgot this term up here. And so on all the way down to this term. But what we notice is we have a 2 squared, but then here I have a 1 over 2 squared, so those cancel out. I have a 3 cubed here, and then a 1 over 3 cubed here, and that will cancel out. There's a 4 to the 4 here. The next term will be 5 to the 5 over 4 to the 4, so that would cancel out as well. And so out of these numbers in the front, the only thing that's going to be left is n to the n. And then what am I left with these a's? Well, I've got a2 times a3 times a4 times so on, all the way down to an. But in the question, we're told that those have product 1. So this is just going to be n to the n times 1. And so I've got the x must be at least n to the power of n. And we're almost done here. All we need to do is show that x can't be equal to n to the n. And to see this, well, if x was equal to n to the n, we need all of these guys here to have equality here. But that's impossible, because if we want equality here, we need these guys over here on the left side to have equality. But that would require a2 equals 1, a3 equals a half, a4 equals a third, and so on. And an would equal 1 over n minus 1. But this actually is impossible, because then otherwise they would, when we multiply them together, we wouldn't get 1, unless, n was 2. But n can't be 2 because n is at least 3. And so therefore it's impossible to have equality on all of these, and so at least one of these inequalities is a strict inequality, and therefore this guy is actually a strict inequality. So I get x must be bigger than n to the n. And that solves our problem. So this is a really, really nice solution, and I don't know, it just made me chuckle that in the solutions, I guess they weren't actually the official solution, so I stole this solution off of Evan Chen, so thank you for providing the solutions. And in his notes, he wrote, try the dumbest thing possible, and I don't know, made me giggle that that was written there. But yeah, this is actually obviously not super obvious to use the AM-GM inequality, but in these sorts of competitions in the IMO, AM-GM inequality is bread and butter for the contestants who are sitting this, and that's probably one of the first things they would try. So considering this is an IMO problem which is supposed to take several hours to solve, I think a lot of students would have gained quite a few marks here. Anyway, thank you for watching. If you are new to the channel, please do consider giving this video a like and also subscribing as well. It helps with the algorithm and all those sorts of things. Anyway, I'm going to stop waffling. Thank you for watching. I'll catch you in the next one. Have a great day.